We're going to now talk about how an image is represented in the computer, how a color image is represented in the computer, and how a video is represented in the computer, and the very important concepts of sampling and representation and quantization. It's always very good to have in mind the images that we normally take with our cameras. But please remember what we see here, and we talked a few videos ago, that the images that we are familiar with is just a very small part of the spectrum of images that we can acquire at different wavelengths and with different modalities. And the concepts of sampling and quantization are relevant for basically all of those modalities. We're always going to have to sample, we're always going to have to quantize. But again, it's good to have in mind when we talk about these different ideas, how they apply to the images that we are most familiar with, which are the images from our own digital cameras. So the basic idea is as follows. We basically have light basically reflecting on the objects. And the light that is reflected on the objects goes into the camera. And what we have are sensors in the camera, as we can see here. Remember, in our eyes, we have the retina, and the retina are the cones and rods. Those were the sensors. In digital cameras, we have sensors, exactly the same way as we have sensors in our eyes. So this is just one example of a sensor. The energy is coming in, there are filters, and then basically the energy is acquired and is transmitted. So the energy is sensed and transmitted. And normally what we're going to have on a regular camera is a two-dimensional array of these sensors. So each one of these is going to be one of these. Okay? And normally they are arranged in a square or rectangular fashion as we see it here. So we have actually kind of a discrete number, and that's when we go and buy digital cameras, we hear that this is about 1000 by 1000. It means actually, we're going to talk a bit more about that in a second. It means that we have 1000 sensors in this direction, 1000 sensors in this direction, so a total of 1000 square sensors. So once again, light is reflecting objects, is projected into the camera, and is sensed by the camera. But all the process has a step of discretization. Some of you might be more familiar than others with this. Those of you that took classes in digital signal processing and are aware of A to D converters, this will be very simple and very familiar to you. But let's just review it for those that are not so familiar with the concepts. So we see here the light represented here is reflected from the object, and it goes into the sensing device. Think about your digital cameras. So this is a blown up of what we have back here. It looks, the object is continuous space, everything is continuous, but we actually get a discrete representation of that object. And the discretization applies in two different directions. One is a spatial discretization. So we have a discrete number of sensors here. And basically the light, one of the simplest modes is that we integrate, each one of these integrates the light arriving to it. So that's a discretization in the space. There's also discretization in the amplitude. We're not going to be able to capture every single level of gray, every single level that is reflected from the object, but we're going to have to discretize it as well. So let's talk a bit more about that. This is the object as we actually see it. And let's just look at one line across this object. So we see that it has different values. It goes from white to gray. So let's just now draw the profile, which is what we see here. So it's very light, white, and then it becomes a bit dark. And if we see here, let me just erase this so we can basically see it more clearly. If we go around, I'm going to just mark it here. If we go around, we see that it's going for white, then it's dark, then it just becomes brighter a bit and goes down again, and then it's white again. So it has kind of this profile. High is white, then it goes dark, and then it goes up, down, and then it becomes white again. Of course, it's not perfect. It has some noise. Even when we go and buy paint and paint a wall, basically we think that it's exactly the same color, but it's actually not. It has some small variations which are represented here. So again, there are two processes happening here. One is sampling. we are going to basically look at the values at certain discrete intervals. We are not going to have the values all around. We're going to have it at certain intervals. Okay? That's one discretization. The second discretization is we're not going to be able to represent every single possible value here. We're going to basically just represent a few of them. We're going to round them. So let's just give an example, a very simple illustration of how can we round. Let's say that we see the value 17.5. So basically we see that this is the value that is representing a particular gray value here. So how can we round this? One way is just to truncate it like this. And then basically say, I know that what came into the sensor is 17.5, but actually I'm going to represent it by 17. Okay? So there are more ways of doing this, and we're going to talk in detail about quantization. This is sampling, and discretization in this direction of the gray values is called quantization. We could also consider, for example, if we had 17.5 as before, we could actually divide it by 2, take this, and multiply by 2. So basically we divide it by 2, then we round, and then we multiply by 2. And I'm going to just ask you, as a very simple exercise, what's this value? And what will happen if instead of dividing by 2, we basically, for example, divide by 4. Round down, and then multiply by 4. And I'm going to have you think about this. It's a simple arithmetic operation. We're going to discuss a lot about this particular operation in the chapter on quantization. But to recap, we have two ways of sampling. One is the two basic ways of discretization. One is sampling in the spatial domain, and the other is quantization in the gray values. So the basic idea is that while we have started from a continuous object that basically lives in the whole space and has multiple gray values, we end up with a discrete object that has discretization both in the spatial domain and also in the gray values. The whole idea of good digital cameras is to have a dense enough sampling here and very, very fine level of quantization, so we don't notice that everything is discrete, but it is discrete. So we have pixel values. Each one of these is called a pixel. This comes from picture element and is denoted as pixel. And actually, I'm gonna just, if you want to Google or you want to search on the web a bit, you might find it entertaining to find out who basically was the first person to use the term pixel. It's actually a very famous statistician, and you can have fun looking for that on the internet or discuss about that in the blogs when you find out about that. So every one of these is discrete, both in space and is discrete also in its gray values. And that's how we get pixels. And once again, the more we have of this and the more we have of the levels, the better the image it is. So regular images will be, for example, 256 by 256 spatial domain. That will mean that it will have 256 square pixels, and maybe it's represented by 8 bits. So every pixel is represented by 8 bits, which means that it can represent 256 different gray values. And we're going to see how important this is. Both the spatial discretization and the quantization of gray values are extremely important. We can have better images. Let me just go back. We're going to have, for example, we might have an image that has, instead of 256 by 256, it might have 512 by 512, and still 256 levels. So it's going to take more memory to save that image, but it's going to have a better quality. And once again, when you're buying digital cameras, they normally tell you a lot about this number, how many pixels it has. And that tells you how fine the sampling is. We want a lot of pixels, so they're so close to each other that we can actually believe that it's a continuous domain. And the same at the level of the gray values. So once again, each one of these is a pixel and it's represented by gray values. Now this is a black and white image. We actually, in our cameras, we have color images. Color images are represented by 3 of these images. One for red, one for green, and one for blue. So basically the cameras acquire, I'm going to explain a bit more about that in a second, acquire 3 images. One represents the blue colors, how much blue there is in the scene. The other represents the green, and the other represents the red. And this is called red, green, and blue. So you're often going to hear images which are R, G, and B. I should make one comment about this. Most low-end to mid-end consumer cameras, they actually don't really capture full 2-dimensional arrays for each one of the colors. So we would like to have each one red, green, and blue. So that's what we would like to have. Red, green, and blue. That would be the ideal scenario, and the more expensive cameras actually do that. Basically, they capture 3 full images. Most consumer cameras, if you buy a low-end digital camera, actually does something slightly different, something that is called mosaic. And the basic idea is that it captures the pixels with interleaving in the colors. We capture a red, a green, a red, a green, and so on. And here, it will capture a red here, a blue, blue, red, and so on. So the next one will be red, green, red, green. The next one will be blue, red, blue, red. So actually, it's not having the tripled amount of pixels, it's actually having 1 pixel red, 1 green, 1 red, 1 green. From this, we're going to have to interpolate, and that we're going to learn how to do those things in the 3rd and 4th weeks in this class. We're going to have to go, because to represent a full color image, at every pixel, we're going to have to go red, green, and blue. So we do have the red, we're going to have to create somehow the green and blue, and that's done from the neighboring pixels. Here we have the green, we're going to have to create the red and the blue. So we are going to have to complete the 3 channels to be able to see a color image. When you buy digital cameras, they actually normally tell you the size on this, which is the size after they have done that interpolation, although as I said, the regular consumer images capture this. So they actually capture 1/3 of the data that they tell you that they're giving to you, that the data they tell you they're giving to you has been interpolated from what has been captured. So we have discrete images. We have a red, green, and blue channels. We're going to think about them as red, green, and blue. So we already went from this representation to the interpolated. By the way, this is called mosaic. So that's how color images are created. Now, how are videos? So this is how you have an image in your computer. You have 3 channels, 3 arrays of 2-dimensional discrete values, 1 for red, 1 for green, 1 for blue. So what happened with videos? Videos basically repeat this. So one image has red, green, and blue. And what happened in video, you have multiple of these. For example, for 1 second of video, in some of the formats, you're going to have 30 of these. So you're going to have 30 times R, G, and blue. And each one of these, remember, is one of these 2-dimensional structures. So basically, if you want to have 1 second of video in your computer, you have 30 times 3 images. 30 images in 1 second, and 3 because you have 3 colors. So in 1 second, you're going to have 90 images of this type to represent 1 second of video. And of course, 90 images, so let's say 90 images at a resolution of 512 times 512 each, and 8 bits each. So this is what you need to represent at relatively low resolution. This is not very high resolution. This is pretty standard. But basically, this is what you're going to need to represent 1 second of a video in your computer. By the way, instead of saying that is 3 times 8 bits, 3 times because we have RGB, sometimes people will say that our resolution is 24 bits. So we use 24 bits to represent basically a pixel. Okay, so this is how you have. If you go now to a computer that knows how to deal, a program that knows how to deal with images, you're going to see basically 2-dimensional discrete arrays, as many as seconds or frames you have in your image. Each one of these 30 is called a frame, and you have 30 of these in a second, or 30 images. When we talk about still images, we talk normally about images. When we talk about videos, each one of these, we call it a frame. So this is how your images are represented. Let's just look a bit more about how important and what are the effects of your resolution in space and your resolution in gray values, meaning how many pixels you're going to have and what are the gray values that you're going to use for them. So this is again the same type of representation. This is how one color of one image or one color of one frame is represented. If you have the letter D, then these pixels are 0. When we have 8 bits, normally 0 is black, and 1 or 256, 255 actually, is white. So if you are going with 8 bits, you can go from 0 to 255. 0 is black, 255 is white. Sometimes the 255 is called 1 if you want to talk about the interval between 0 and 1. So although you see this, actually in the computer is represented by a bunch of zeros for the black region. Then let's say that this region is in the middle of the gray value. It will be an equivalent of a 128 value or a 0.5 value. So we see here 0.5, and then 1 for basically the whites. So this is your discrete representation of this image in the computer. Okay? At every pixel, you have a discrete value. Now, sometimes one of the things that happen is because you have only 256 different levels that you can use, sometimes your image is too bright and you might not be able to represent the small variations in brightness there. Remember, the human visual system can basically adapt to multiple levels of brightness, but not all of them at the same time. The same for an image. We can capture many levels, maybe 256, but if we have to deal with a very dark region and a very light region at the same time, we are in trouble. And sometimes the very small variations in this light region, we're not going to be able to capture. And that's called saturation. So it's going to look all white because it all got to the 255. Maybe it was above 255. It wanted to be above 255 because it was very bright. So that happens very often. We take images and sometimes we see what's called specularities or very strong reflections, and it looks white. It looks very light. And that's because the image, the sensor, has saturated. So this explains. Now you know why that is happening. You have a discrete amount of levels, a discrete amount of values to represent your image, and this went above and beyond what you can represent with that discrete amount of values. So again, two discretizations, one in space and one in gray values. And look what happened. What's the effect? And you know that because if you have a digital camera, or if you see images on the web, on the internet, you see images at different resolution. So if you were to use a lot of pixels, you might see this. So this means that you have something which is very, very fine, a lot of pixels. And that looks really nice. On the other hand, if you have something which is much more coarse, less dense, so you have less pixels, you're going to see something like this. And it's very clear to see, for example, how this line is very nicely represented here, is not so nicely represented here. You can see very easily the small numbers here, not so easy here. Look at these numbers here, they're not so clear here. So here we only have changed the spatial resolution. We have not changed the number of gray values. Still, let's say we have 256. So each one of these is represented with 256, and each one of these is represented with 256. But we are not able, basically, to represent so fine detail with this as we are with this. And you can think about, once again, if I want to draw a profile, if you want to represent something that has this profile of gray value, and you actually want to discretize that, if you do it very coarse, you're not going to be able to detect that there is a smooth variation in the gray values. But if on the other hand, you're able to put many more layers, you're going to be able to capture its value at many, many points, instead of just at a few. Let me just use a different color. Just as a few values, if you do a coarse discretization. And that's why this image doesn't look as nice as this one, because this captured what was going on at a very coarse levels in the discretization, in the space discretization. Now, similar things happen if you basically do a very coarse discretization of the gray values. So let's just start. And once again, we are not changing the number of pixels. All these 4 images and the 4 images that are going to come next have exactly the same number of pixels. Okay, so actually it's written here, it has 452. I'm going to just make it larger, times 374. All the images. But the first image is displayed with 8 bits, meaning 256 values. So I'm going to just write it. Maybe I'm going to just say it here. The first is 256, and we actually see it very, very smooth and very, very nice. Here, we only use 7 bits or 128 values. So basically, the values 0 and 1 become 0. 2 and 3 become 2. 4 and 5 become 4. Okay? The easiest way to do that is you take every value here, let's say a value, you divide by 2, you take basically the closest integer from below, and you multiply it again by 2. Okay? So for example, if the value of this image was 8, you divide by 2, you take divide by 2, divide by 2, that's 4. Okay? You multiply by 2, you got 8 again. No problem with that pixel value. Okay? But what happened, let's just do that here. What happens if you have 9? You divide by 2. That's 4.5. But I have to take the closest integer from below. That's 4. I multiply by 2. And this became 8. So a 9 was transformed into an 8. And that's basically reduces the range and reduces the quality of the image. This becomes even worse if we go into this region where we are actually only using 64 different values. So that's equivalent basically to dividing by 4, then truncating and multiplying by 4. And that means that you're going to start talking about basically, if you have only 64, every 4 values are represented with one number. So 0, 1, 2, 3, they all become 0. 4, 5, 6, 7, they all become 4, and so on. And then you can keep going, and this is only represented with 32. So I hope that you're starting to see that the quality is deteriorating. In particular, if you look at lines here, you start to see what's called false contours. You see these lines that they're not clear here. There is a smooth transition here, but here you see these false contours. And that's created because of these jumps that I mentioned to you. So if you were going basically 1, 2, 3, 4, it's actually, you're gonna, when you start taking very, very few gray values, you're gonna go 0, 0, 0, 0, 4. You're gonna jump into that value. And that's because you are basically have much less resources to represent the different gray values. Let's just go into an even more extreme case, and we keep going down. Here, basically, we use only 16, and now I think that you're going to be able to see the false contours very clearly. Here, we go basically only to 8 values. There's only 8 numbers to represent everything that is happening in this picture, okay? And that's basically a very strong quantization. Here, there is basically only 4, and here is basically only 2. In this very extreme case, everything that was below 128 became 0, became black. Everything that was above 128 became 255 white. And then you see a very, very poor quality data. Okay? So that's how the spatial quantization and the gray value, spatial sampling, and the gray value quantization affect you. The more you have of samples, the better quality it is. The more you have the possibility of representing many, many, many small variations in gray values, the better it is. Of course, the more memory it takes into your computer, and that's going to be the subject of our compression unit. So now we know how images are represented in the computer. They're represented as 2-dimensional arrays. Gray level images are represented by 1. Color images are represented by 3, red, green, and blue. Videos are represented by multiples of them, let's say 30 a second. Sometimes it's only 24, depending on the standard that we have, but there are multiple of those images, and as we say, we call them frames. And we know that everything is discrete. So we have sampling and quantization. An image in a computer is nothing else now than a 2-dimensional array of discrete values. Thank you.